Good afternoon, class. We are looking at Chapter 9, Sequences and Series. Here's 9.3, Geometric Sequences and Series. We covered sequences and series, arithmetic sequence and series, and now geometric sequences and series. The objectives are: find the common ratio for geometric sequence, list the term of a geometric sequence, use a recursive formula for a geometric sequence, use an explicit formula for a geometric sequence. Reminding you of what we have covered as far as the series and summation notation is concerned. S sub n, the sum of a sub 1 all the way to a sub n of the first n terms of a sequence, a sub 1, a sub 2, a sub 3. This is sigma. The uppercase sigma is the Greek letter sigma and indicates a sum. The sigma notation, summation of I going from 1 to n of a sub I, means add the terms a sub I beginning with the first term and ending with the nth term. The limits of I to n, that's the indication. I is called the index of summation. A finite series, S sub n equals a sub 1 plus a sub 2 all the way to a sub n. So it ends with n at some point. However, an infinite series, S sub infinity, it's a sub 1, a sub 2, and it continues indefinitely. So the index of summation, I going from 1 to infinity, summation of a sub I. Summation properties: if a sub 1, a sub 2, a sub 3, and a sub n, as well as b sub 1 all the way to b sub n are two sequences, and c is a constant, then for every positive integer n, the following is true. These are some properties that we should be comfortable with. For example, summation of c is nc, so on and so forth, that we have covered. These are important properties we should know. As far as arithmetic sequence is concerned, an arithmetic sequence, each term after the first one is found by adding a fixed number called the common difference, sometimes they call it distance, to the previous term, is an arithmetic sequence or arithmetic progression. So a sub 1, then add d, a sub 1 plus d, that would be a sub 2. A sub 3 would be a sub 1 plus 2d, and so forth. So in general, a sub 1 plus n minus 1 times d. The difference d between consecutive terms is constant, and the sequence can be defined by, if we go with recursive format, a sub n plus 1 is a sub n plus d. If we go by explicit format, a sub n equals a sub 1 plus n minus 1 times d. As an example, 1, 5, 9, 13. As you can see, there's a difference of 4, add 4. The nth term is given by a sub n equals a sub 1 plus n minus 1 times d. The sum of the first n terms is given by s sub n equals n over 2, a sub 1 plus a sub n, or n over 2, to a sub 1 plus n minus 1 times d. And here's the synopsis of what we just covered. Arithmetic sequence. And now section 9.3, geometric sequences and series. A geometric sequence or geometric progression is a sequence in which each term after the first is obtained by multiplying the preceding term by a constant non-zero real number called the common ratio. So geometric sequence is in the form of a sub 1, a sub 1 times r, a sub 1 r squared, all the way to a sub 1 r to the power of n minus 1. That's the general term, where each term is r times the previous one, can be defined. If we want to go with the recursive format, recursively by a sub n plus 1 equals r times a sub n. So if you want any term, the previous one times r. Explicitly by a sub n equals a sub 1 r to the power of n minus 1. As an example, 1, 4, 16, 64. As you can see, 1 times 4 is 4, 4 times 4 is 16, 16 times 4 is 64, and so on. Sum of the first n terms of a geometric sequence S sub n is a sub 1 times 1 minus r to the power of n over 1 minus r, where r is not equal to 1. And so again, here's the synopsis of what we just mentioned regarding a geometric sequence. A sub n is a sub 1 r to the power of n minus 1. Explicitly, a sub n plus 1 equals r a sub n recursively, and S7 is a sub 1 times 1 minus r to the power of n over 1 minus r when r is not equal to 1. Now, let me remind you of the proof that we have seen before. As far as a geometric series, when we add sequences, it becomes a series. So a plus ar plus ar squared all the way to ar n to the power of minus 1. We want to add them up and see what we get. Of course, a cannot be 0. So as far as s sub n is concerned, we write the same thing here. Okay, all the way to n would be ar all the way to ar to the power of n minus 1. This is the summation of the first n terms. Let's multiply both sides by r. So multiply this one by r, and then this becomes ar squared, ar cubed. But this one becomes ar to the power of n minus 1, and this one becomes ar to the power of n if we multiply everything by r. Let's subtract in the following manner. We're going to say s sub n minus r s sub n. So if we subtract this from this one, so what happens is that these terms cancel out all the way to here. Notice this one and this one are identical, they cancel each other. So we are left with the first term of s sub n minus the last term of r times s sub n. And so on the left side, we can factor s sub n out. On the right side, we can take the a out. And now if we divide both sides by 1 minus r, we get s sub n equals a times 1 minus r to the power of n over 1 minus r. That's a proof. So sum of the first n terms of a geometric sequence is what we have here. Now, what happens is if r is a fraction, normally they say between 0 and 1, but if it's between negative 1 and 1, as n goes to infinity, this goes to 0. So if r is between negative 1 and 1, if this number, for example, if you pick 0.5 or 1/2, to the power of 2 becomes 1/4, to the power of 3 becomes 1 over 8. So it becomes smaller and smaller. As n goes to infinity, r to the power of n goes to 0. So you get a times 1 minus 0 in the numerator, or simply a in the numerator. And we get a over 1 minus r. So as n goes to infinity, as n goes to infinity, r to the power of n goes to 0 because it's between negative 1 and 1. So if r is between negative 1 and 1, the infinite sum, the geometric series converges because the limit does exist. Show that the sequence is geometric, list the first term and the common ratio. And that's basically how it goes. In order for you to prove a sequence is geometric, first you come up with the first term. Obviously, the first term is 2. Then you come up with the ratio and make sure it works. If you divide 8 by 2, you get 4. Now, does that work for the rest of them? It's important to know. 2 clearly is the first term. And then divide 8 by 2, 4. We are claiming this is to be r, but all you have to do, 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128, and move on. So it does work. What about the sequence S sub n, which is 3 to the power of n plus 1? The best course of action is to write the first few. For example, if n is 1, you get 3 squared, which is 9. If n is 2, you get 3 cubed, 27. If n is 3, you get 3 to the power of 4, or 81. So clearly the first term is 9. And as you can see, if you divide 27 by 9, you get 3. So 9 times 3 is 27. 27 times 3 is 81. And so on and so forth. So A1 is 9, R is 3. Again, just to make sure we are following that. In this case, for example, R would be 8 divided by 2. In this case, R would be 27 divided by 9. In this case, we do the same thing. Let's write out the first few terms. If n is 1, we get 3 times 2, 6. If it's 2, 2 squared is 4 times 3 is 12. If it's 3, 2 cubed is 8. 8 times 3 is 24. Which clearly says the first term is 6. What about the R? 12 divided by 6 is 2. And as you can see, 6 times 2 is 12. 12 times 2 is 24, and so on. So again, what is R here? We would say 12 divided by 6 is 2. And you check it, of course. Remember, just divide 12 by 6 and keep on checking. Find a sub n and a sub 5 for the geometric sequence 4, negative 12, 36, negative 108. So you have to, if you are claiming it's a geometric sequence, you have to know the first term. Clearly, the first term is 4. And then you need to find R, so divide negative 12 by 4 and check it. In other words, this is negative 3, by the way. Negative 3. So 4 times negative 3 is negative 12. Negative 3 times negative 12 is positive 36. Positive 36 times negative 3 is negative 108. So it does check. You must check. And now we're going to find a sub n and then a sub 5. A sub n has the formula a sub 1, which is 4, times r, which is negative 3 to the power of n minus 1. So we're going to stick with this. That's the general term. What about a sub 5? So replace the n with 5. When you do that, of course, 5 minus 1 makes it 4. This is positive 81. 4 times that is 324. Find its recursive formula. So you want to use that. A sub n plus 1 is r, which is negative 3 times a sub n. So r, which is negative 3 times a sub n. Simply put, multiply any term by negative 3, you get the next one. That's what it says. We want to find this sum, the summation of 2 times 3i as I goes from 1 to 6. So if you replace the I with 1, you get 2 times 3, 6. If you replace it with 2, you get 3 squared, 9 times 2 is 18. If you replace it with 3, 3 cubed, 27 times 2, 54. So clearly, we recognize this as a geometric series. There isn't a series because we want to add them up. Sum means add them up. This is a geometric sequence, everybody. When we add them up, it becomes a geometric series. And so the first term is 6, and R just multiplying by number 3. So clearly, we have a geometric series. The first term is 2 times 3 to the power of 1, which is 6, and R is 3. Notice again, 18 divided by 6 is 54 divided by 6, or 6 times 3, 18 times 3, and so forth, so on and so forth. And with that being the case, we can use this formula because we want the sum of the first, how many terms? N is equal to 6. So S sub 6. So this is equal to S sub 6, and replace the N with 6, A sub 1, also 6, R is positive 3. So this is obviously negative 2. This is 1 minus 729. This becomes negative 3. This becomes negative 728, and it's 2184. The rest is basic math. So this is the formula that matters, everybody. So we want to make sure that we understand that one. So the rest is really not a big deal. Right? All right, let's move on. Find the sum of 3 over 5 to the power of I as I goes from 1 to infinity. Again, let's write the first term. I is 1, we get 3 over 5. Replace the I with 2, you get 9 over 25. Replace the I with 3, 3 cubed, 27 over 5 cubed, 125. So we have a geometric series because we are adding them up, with the first term being 3 over 5, and the R happened to be 3 over 5 also. I hope you recognize when you have it in this format, this is also the R, or just simply put 3 over 5 times 3 over 5 times 3 over 5, or divide this one by this one. So A1 or A and R is 3 over 5, both of them. Now, because R is between negative 1 and 1, everybody, since this is the case, we can use this one because we want S sub n as n goes to infinity. So this is the formula we're going to use, or simply S sub infinity if we want. So replace this one with 3 over 5, this one with 3 over 5. You can call it S sub infinity or even S sub n. And this is a simple case, everybody, of a complex fraction. So if you multiply the top by 5 and the bottom by 5, then the numerator simply becomes 3, and the bottom becomes 5 minus 3, which is 3 halves. So it's very straightforward. I hope everybody is fine with that. And nobody has any problem with complex fractions. We are going to move on. All right, we want to add these terms, class. And what do we notice? We are adding 1/2 to 1/4 to 1/8. We notice this is geometric series, or can even say geometric sequence, then you add them up, geometric series. The first term is 1/2. Then you multiply it by 1/2 to get 1/4, by 1/2 to get 1/8, by 1/2 to get 1/6, 16. I hope you recognize that. Let me write that. So 1/4. If you divide 1/4 by 1/2, you do get 1/2. So the first term and r are both 1/2. Sometimes they call it a, sometimes they call it a sub 1 class, okay? Again, in some texts they just use a, okay? In some texts they use it as a sub 1. In any event, so with that being the case, let's put it back into this equation, or into this equation. A is 1/2 over 1 minus 1/2. And that you really might say this is 1/2, so 1/2 over 1/2 is 1, or you might multiply the top and the bottom by 2. Either way, you end up with 1. This is a complex fraction. It might be easier that you say 1 minus 1/2 is half, so 1/2 over 1/2 is 1. Either way, you should have no problem coming up with the answer easily. Another way we can use a geometric series is when we deal with repeating decimals. So we want to express 0.46 bar as a rational number. And we want to use the information from a geometric series. So first notice 0.46 bar means just keep on repeating 46, 46. There are two decimals that are being repeated. So if you look at this part only, this means 46 over 100 or 0.46. This one means 46 over 100 squared or 0.0046. And this one means put 4 zeros and then 46, or 46 over 100 cubed. So we can write it in this format or in this format. Again, I want you to notice both ways, fractional format or decimal format. I want to discuss the decimal. It might be easier to see it first. It's 0.46 plus 0. This part is 0.0046, and this 2, 0.0000, and then 46, or in this format. Either way. So it's a geometric sequence with the first term being this one. Again, either decimal or fraction. And I'm not going to simplify the fraction yet, although remember, when you deal with fraction, you must put them in lowest term, but I want to make a point here. So the first term is 0.46 or 46 over 100. And or I hope you recognize that this one is 100 times larger than this. So that means the fraction is 100 times smaller. So r is over 1 over 100. 1 over 100. Or if it's easier to see it from here, r is 0.01. It's 100 times smaller. That's the meaning of it. Or divide this number by this one, divide this by this one, you get 1 over 100 or 0.01. Therefore, we can use the easy way out. A over 1 minus r, where A is this number or this number, or is this number or this number. I'm going to write it as a complex fraction. If you were to use decimals, this would be 0.46. This would be 1 minus 0.01. Doesn't make any difference. I'm going to quickly show you both ways. As a complex fraction, you multiply the top by 100. You multiply the bottom by 100. Okay, so this is 1 minus 0.01. So when you do that, I hope you recognize that the top becomes 46. Let me use a different color. And the bottom, when you multiply these two, you get 100 minus 1, or you get 99. And the reason I'm using that, because we want to write it as a rational number, that they're saying that just write it as a fraction in essence. That's why. However, if you put 0.46 over 1 minus 0.01, again, I want you to see that format as well. If I go with 0.46 divided by 1 minus 0.01, I get 0.46 divided by 0.99, which is the same thing. And again, both ways are absolutely perfect. However, you can't leave it like that. This would be the final answer. And as always, you check it to see if you can simplify it further. It can't be simplified. You're done. A population of fruit flies is growing in such a way that each generation is 2.5 times as large as the last generation. Suppose there were 1,000 insects in the first generation. How many would there be in the fifth generation? What is the total population after the fifth generation? So we notice that we are dealing with a geometric sequence such that right away R is 2.5. It's getting larger by a factor of 2.5. And so what is this is A sub 1. So we have a geometric sequence. R is 2.5 and A sub 1 is 1,000. And we want to know how many would there be in the fifth generation. That means we are going to use A sub n, and we are interested in finding A sub 5. Which is A sub 1 r to the power of n 5 minus 1, which makes it 4. So we replace the A sub 1 with 1,000, r with 2.5, and we put this into a calculator. So we raise 2.5 to the power of 4, and we multiply it by 1,000, we get this number. And because we are looking at the number of population, we have to round it to the nearest ones. And this, because next to it is 5, it goes up to 3. So it becomes 39,063 fruit flies. So how many are there in the fifth generation? This much in the fifth generation. What is the total population after the fifth generation? Now we use S sub n. And we want S sub 5. Of course, A sub 1 is still 1,000, R is still 2.5. Now we have to put this into a calculator, meaning 2.5 to the fifth power. Subtract it from 1 multiplied by 1,000 divided by 1 minus 2.5, which is negative 1.5. But please understand the numerator is also negative. The result is positive. And again, we do the rounding. We want to round it to the nearest ones, which is 7. Next to it, we find 5. So we go up and we make it 64,438. That would be the total population of the flies, fruit flies, after the fifth generation. Find R and A sub 1 for the geometric sequence, with third term being 20 and sixth term being 160. In essence, we are dealing again with the system of equations. So here's the given, everybody. A sub 3 is given as 20, A sub 6 is given as 160, and we are going to use the formula for A sub n, which is A sub 1 r to the power of n minus 1. And so using that, this becomes A1 r squared equals 20. This becomes A1 r to the power of 5 is 160. So we use this formula for A sub 3 as well as A sub 6. Now, we are dealing with the system of equations here. So we have two equations. We want to solve for A sub 1. And in essence, let me just actually do this one more time. In essence, you need this part only. Okay. You need this part. And the methodology for a case like this is division. When you divide, you can get the answer. So you divide the bottom by the top in essence. Okay. So we're going to divide this line by this line. So A sub 6 over A sub 3 is A sub 1 r to the power of 5 over A sub 1 r squared, which makes it r cubed. And r cubed is 160 divided by 20, which gives us 8. So if r cubed is 8, r must be 2. So if r is 2, just use the first one or second one, it makes no difference, and find the missing a sub 1. So if a sub 3, which is a sub 1 times r2 squared is 20, and r again is 2 squared or 4, and divide both sides by 2 squared, which is 4, and a sub 1 becomes 5, and we have the first term and the ratio r. We are done. Express 5.75 bar as a rational number. You remember when we dealt with the repeating decimal, we are going to rewrite this as 5.757575. And what happens is that you basically notice this is 5 plus this part. And this part I have shown you, there are two ways to write it. I can write this one as 75 over 100 or 0.75. This second piece as 75 over 100 squared or 0.0075. And this two as 75 over 100 cubed or 0.0000 and then 75. Either way is fine. And what we are going to look at, this 5 is not going to go anywhere. We are going to do this just as we did before. So this part, just as the previous example, is following a geometric series, with the first term being this one or this one in any format that you want. And r, again, notice this is 100 times larger, so the fraction is 100 times smaller. So you can say r is 1 over 100 or 0.01. And because this is between -1 and 1, we can use this method to come up with the answer, everybody. Just as the previous one. So we are going to use that, and we're going to write 5.75 bar is 5 plus 0.75 bar. And this part uses this formula, A, which is 75 over 100, over 1 minus R, which is 1 minus 1 over 100. This one, again, I'm going to write both methods. I'm going to write the decimal, 0.75, and this one I'm going to write 1 minus 0.01. Both ways is fine. Let's look at the complex fraction and multiply by 100, the top and the bottom. And this part is 75. And this part is 100 minus 1 or 99. Let's continue with that thoughts. And 75 over 99, they are both divisible by 3, becomes 25 over 33. Because they said rational, sometimes they want you to combine them. So 5 times 33 plus 25, they want you to put it in this format, improper format, instead of a mixed number. Either way is fine with me. Just want to follow that. If you want to go with the decimals, everybody, this would have been, the numerator is 0.75, and the numerator, the denominator 1 minus 0.01 would be 0.99. And please understand this part the same as this part, because you have to change it accordingly. And again, just choose the one that is easier for you to deal with. This is an interesting question. How much will be earned on day 20 if daily wages in cents follow the sequence 1, 2, 4, 8? So we have 1 cent for the first day. The second day, they're going to multiply it by 2. We get 2 cents for the second day. Then you multiply it by again 2, you get 4 cents the third day, and so on and so forth. So we have a geometric sequence. We want to add them up, becomes a geometric series where the first one, a sub 1 is 1 and r equals 20. Okay. And we want a sub 20. Okay. Because we want to see how much we get on the day 20, and then we're going to get to S 20. Okay. So a sub 20, we are going to go with this formula. Okay. And replace the a sub 1 with 1 or with 2, which is simply 2 to the power of 19 cents. 2 to the power of 19 cents. You put it into a calculator, you get this one, you drop 2 decimals, and it becomes in dollars. So these 2 become decimals, okay? So we have $5,242.88. This is the power of a geometric sequence. How much do we have all together after 20 days? That means calculate S sub 20. That's the meaning of that. And so we are going to use this formula, and we want S sub 20. We are going to replace the A sub 1 with 1 and R with 2 for the top as well as the bottom. The denominator is -1, easily. The numerator, 2 to the power of 20 subtracted from 1 becomes negative over negative is positive. You put it into a calculator, you get this number with 2 decimals. We're going to go with decimal here. You get $10,485.75 if we just received 1 cent the first day, and then we doubled up the first 20 days. Over the course of 20 days, we get over $10,000. That's amazing. That's really amazing. All right, an infinite geometric sequence. Find the formula for the general term a sub n of the sequence 1, -1/3, 1 over 9, -1 over 27, 1 over 81. We have the first term as 1, and then notice it becomes r equals -1/3, becomes a geometric sequence because you're multiplying by, if I multiply this by -1/3, I get -1/3. Multiplied by -1/3 again, you get positive 1 over 9. Multiplied by -1/3, you get -1 over 27. Multiplied by -1/3, you get positive 1 over 81. So you have to check. So that's what we have. And so the formula would be a sub n equals a sub 1 r to the power of n minus 1. So let's plug in. Let's plug in a sub 1 is 1 and r is -1/3. So this is the answer. However, this one has no bearing. Normally, they like to separate the negative sign from the rest of it. So this is -1 to the power of n minus 1 and 1/3 to the power of n minus 1. This is an alternating sequence. And you really have to check. So check. Remember, a to the power of 0 is 1, right? So if I put 1 here or here, makes no difference. If I put 1 here, 1 minus 1 is 0, -1 to the power of 0 is positive 1, 1/3 to the power of 0 is also 1. So I hope you recognize the first one works. And of course, you really have to check with number 2, number 3. I'm going to leave it for you to check it. Replace the n with number 2. I hope you recognize 2 minus 1 is -1, -1 to the power of 2 minus 1 is 1, -1 to the power of 1 is -1, 1/3 to the power of 2 minus 1 of 1 is 1/3. So it does become 1/3. So you really should check. So the tip again, reminding you for alternating sign, either start with -1 to the power of n or -1 to the power of n minus 1. And in this case, the reason it's actually n minus 1 because the first term happened to be positive. And as I mentioned before, if instead of n minus 1, for the sake of an alternating case only, if you use n plus 1, it works out the same way. And you can do that for this part, but not for this part. It's important to understand when and where to use that. Another application, an interesting question, which becomes an infinite geometric series. The first swing of the pendulum is 25 centimeters, and which represents an arc length. If each swing is 75% of the preceding swing, what is the length of the arc of the 11th swing? We have a geometric sequence. A sub 1 is 25 centimeters, the first swing. And then if each swing is 75% of the preceding one, normally it's more than that, but just for the sake of argument, it's 0.75. It depends on the amount of friction, by the way. And so for the 11th swing, we are going to use a sub n, more specifically a sub 11. So a sub n is a sub 1 r to the power of n minus 1. We want a sub 11. So into this formula goes a sub 1 equals 25, n is replaced with 11. So 11 minus 1 makes it 10. You raise 0.75 to the power of 10 and then times 25. You get 1 point something. And if we stop, let's say here, next to 7 is 8, we take it to 1.408. As far as the number of decimals, you always want to pay attention as to how many they ask you. If they don't, you have to go with many, many, many decimals. So you really should go with this one rather than this. How far, or what is the total distance, does the pendulum travel after 15 swings? So we want the total amount of distance. That means we want S sub n, n is 15. We want S sub n, n is 15. So replace the A sub 1 with 25 or with 0.75 and n with 15. Of course, you got to put it into calculator. Clearly, the bottom is 0.25 raised to the power of 15, subtracted from 1. It gives you that number, 0.98666. 25 cancels out the 0.25, and it gives you 100. So this is gone, and this is 100. Okay, so that's easy, actually. And then this one, you get 2 decimals, okay? And so you get 98.66. I didn't write the rest of them, 4 centimeters, and so forth, okay? How far does the pendulum travel before coming to a rest? In other words, before it stops. Now, we want, in essence, as n goes to infinity, we want this. And the reason we want this because r is between -1 and 1, r is 0.75. Because r is 0.75, we are going to use this one, everybody. Again, this is at any point. This is when n goes to infinity and r is between -1 and 1. You should always use that. If n goes to infinity and r is between -1 and 1, it's convergent. If r is not between -1 and 1, it goes to infinity. I want you to know that the value for this would be infinity if r wasn't between -1 and 1, but it is. So replace it. So this is 0.25, and 25 divided by 25 is 100. I use the proper units. Okay, remember it was centimeters. So it covers 100 centimeters before it comes to an end, to a rest, to stop. Use a graphic utility to find the sum of the first 15 terms of the sequence 1/3 to the power of n. That is to find 1/3 plus 1/9 plus 1/27 all the way to 1/3 to the power of 15, or the summation of I from 1 to 15, 1/3, 1/3 to the power of k minus 1, or simply 1/3 to the power of k. Again, that's one way to find it. Okay. I should actually use I here. This must be the same as this one. Okay. So that's I, everybody. All right. So that's, I mean, we've seen it as far as the uh, formulas are concerned, but the methodology of using a graphing calculator, for example, TI-84, which looks like that, get to the list by pressing second and stat. So this is the second and stat. Okay. And you go to the right, you get to math. Okay, press sum, look at them. You go to the right, you go to math and look at them, and sum happen to be, in this case, number 5. And then get to the list by second and stat again and right to up. So you do it again, and then instead of math, you go to the middle one, okay, which is operations. And again, notice you come down to number 5 and you press sequence. And when you press sequence, then it gives you the expression, the variable, start, and step. So you press the sequence, you put the expression in there. Okay, that's the expression, the variable x or n, it doesn't matter. We start with what number? We start with 1. Normally we start with 1, but if the starting point is not 1, whatever that you needed. So where it says start, you put the lower limit of your summation, and upper limit, in this case, is 15 of your summation. Step is 1. It's the increment, and it's always 1 in the case of a summation. And then you press paste. So notice what we put. For the expression, we're going to put 1/3 to the power of n, or in this case, x. The variable is x. As long as these two are the same, and that's fine. And we use x here because that's what you see here. Start with 1, end with 15, and the step is 1. Okay. Paste. When you do that, it says sum, it shows sum, sequence, 1/3 to the power of x, and so forth. And the answer is what you see. If you use a different TI, some older ones, then they will not give you this part. They will not give you this part, and you have to put this in there right away in this manner, and it gives you the same answer. So that's using a graphing utility to find the sum.